Welcome everybody to the third week of discrete mathematics. In this week we will be continuing our study of proof techniques, and in particular we will look at the proof technique of contradiction and contrapositiveness. So to recall, we were dealing with the techniques of proving a statement like A implies B. There are many proof techniques that can be applied for proving A implies B, namely constructive proof, proof by contradiction, contrapositive, induction, counterexample, existential, etc. Now this is something I have told again and again in all the video lectures regarding proof techniques, that which proof to apply depends on the problem. In this course, we will be giving you all the different proof techniques, or at least most of them. But whether to which proof technique to apply for which problem completely depends on you. Sometimes the problem can be split into smaller problems, and that can make it easier. Sometimes viewing the problem in a different way can make it easier. But whether to split a problem, or how to split a problem, or how to look at it in a different way is an art that has to be developed by you. In other words, there are some thumb rules that we will give. For example, if the problem is of this kind, then this kind of technique can be helpful. But at the end of the day, which proof technique to apply depends fully on your skill that you have to develop by doing a lot of practice. Now till now we have seen some of the tricks. The first thing that we saw was how to split a problem into smaller problems when the B, that is the deduction, is of the form C and D. So in other words, if B is of the form C and D, then A implies B is same as proving A implies C and A implies D. We saw an example how to use this particular way of splitting the problem can help you to split a problem into two parts. We saw one such example. The next technique that we learned was that sometimes reducing assumptions can be helpful. In other words, there can be assumptions that are not necessary and we can throw them away. For example, if I have been asked to prove A and C implies B, and all that I need is A, and I can prove A implies B, then that means that this C is a redundant assumption and we can safely throw it away. Thus, given the set of assumptions, one has to find out what are the actual subset of assumptions that might be useful. The rest of them can be thrown away. So in other words, A implies B is good enough. A implies B implies A and C implies B. Again, which assumptions are needed and which assumptions can be thrown away depends on the problem, and you have to identify them using your intelligence. Now the third technique or third trick that we learned was that sometimes proving something harder can actually be easier. So in other words, if we have to prove A implies B, and if we can prove that C implies B, then A implies B is follows. So in other words, while it might be harder to prove A implies C, But if we can prove A implies C, then we get A implies B. Sometimes this harder statement is easier to prove. For example, here, notice that A implies C is strictly harder than A implies B. But proving the harder statement can actually be more helpful, more easier than solving the easier statement A implies B. Now moving on, after the set of useful tricks, we looked at the problem and the first major approach of solving a problem, namely constructive proof. The idea of constructive proof is that if we have to solve A implies B, we work with A and start working ahead and end up proving B. Now we split up the constructive proof into two parts. First part was a direct proof, meaning you directly prove B from A. And the second one was this case study, where we split the problems into smaller problems depending on A. To recall, for the direct proofs, either you can start from A and make a step-by-step deduction and end up proving B, or sometimes this direct proof can be quite magical. So we might want to come up with a different technique. The technique that we suggested was that going backwards, namely start with B, start with the thing that you have to prove, work with it and slowly simplify it to get a simpler statement which might be easier to prove from A. So in other words, if you can prove that, if you can simplify B to C, that means C and B are basically equivalent statement, just that C has been more simplified. In that case, proving A implies B is same as proving A implies C. So working with B would help you to, working with B and simplifying it to C will help you to understand how to finally prove A implies C. Since C is a simplified form, so proving A implies C will be easier. Now, in the context of case study, the idea was that sometimes we can split up the problem into cases depending on A. So, in other words, if the statement is of the following, that A equals to C or D, that means C or D implies B, then A implies B can be split up as C implies B and D implies B. So in some sense we can split up into cases, that A is either C or D, and in that case C implies B and D implies B is solved. We saw a couple of examples where we used this case study to solve the problems. So this was what we did till now. Namely, we looked at some of the techniques of splitting the problem into smaller parts and how to go about attacking them. Now in this video lecture, we will be looking at a completely new technique which we call proof by contradiction, where the idea is to view the problem in a different way. So here is the idea. So the idea is that, note that proving A implies B, or this statement A implies B, is equivalent to the statement not B and A is false. So in other words, to prove A implies B, one can prove not B and A is false. is what is called the proof by contradiction. So if you have asked that, okay, assume A and then prove B, then what you are asked to prove or what you can prove is this statement, that namely not B and A is false. From this particular expression that we have, a similar statement can be drawn which is also of this form. That A implies B is equivalent to not B implies not A. This is called the proof by contrapositive, and we will be using this technique after a couple of videos. So in this video, we will be looking at the proof by contradiction in this part, where we will be using not B and A is false to prove some statements. It is a very powerful proof technique, and we apply it quite a lot in our various proofs, mathematical proofs. So what is it that we do in the case of proof by contradiction? A good example is to consider this following example. It's not a mathematical example as such, but it's something that's useful. Say we want to prove that the earth is not flat. Now how do you prove that earth is not flat? One way of going about it is that, okay, let's try to prove it directly. Namely, we say that, okay, when we see a ship coming from the horizon, we see first the top of the ship and slowly the complete ship arises, right? And this follows from this usual proof that we have seen, that if I am standing here and if there is a ship here, first what we see is the top of the ship, and then much later on we see the bottom of this ship. The bottom of the ship appears slowly. And the only way this can happen is that if it is not flat. This is the first technique that one can apply. This is what we call as the direct proof technique. This is the direct proof or the constructive proof. The second way of saying is that, okay, let's assume that the earth is flat. In that case, does something weird happen? Do you get a false statement? So if the earth is flat, when the ship is coming from the horizon, the whole ship will appear at the same time. But that doesn't happen. We see the mast first and then the whole ship, and hence we get a contradiction. Although these two statements look so much similar, but the way in which these two are presented are very different. So this also tells us something important, namely, these proof techniques are not necessarily written on stone. A single problem can have multiple different proof techniques. Now all we are saying is that here there are different kind of proof techniques and you can choose any one of them. And for particular problems, obtaining a proof using one proof technique might just be easier than obtaining a proof using the other proof technique. And that's all that we are saying in this different type of proof techniques. Right? So in other words, proving that the earth is not flat can be done either using the constructive proof or using a proof by contradiction. So let's see an example. see the example, we have to consider primes. And we have to prove that the primes are infinite. In other words, there are infinitely many primes. So, in other words, what we have to prove, we want to prove is that for all n greater than or equal to okay. So let's see an example. So consider this problem of primes. Now what are primes? We know primes are numbers that cannot be divided by any other integer less than itself. So what are the primes that we know of? The primes that are known of are 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on and so forth, right? Now, is it that there is only a finite set of primes? For example, there are only 1000 primes or 10,000 primes or something like that? Or is it that there is always some prime? In other words, we want to prove that there are infinite number of primes. Or in other words, we want to say that the primes are not bounded by any large number. So, for all n, integer n, positive integer n, there always exists a number which is bigger than n and which is prime. So, there is a prime that is always bigger than some number. So, you can pick your favorite n. So, you tell me, okay, is there a prime bigger than 10 lakhs? And I should be able to produce you one. So, this proves that the number of primes are not bounded by a large enough integer. They are infinite. Now, how do you prove this statement? How do you prove that the number of primes is indeed infinite? So, to prove that, we will prove it using contradiction. So, first of all, let's go back one step. If we want to formulate this statement that prove primes are infinite, if I have to formulate in the terms of A implies B, what is B and what is A? So B is clear. So B is primes are infinite, right? Primes are infinite. Now what is A? There is as such no A here. So many times we will get such kind of questions. The A in this case is actually everything that we know to be correct. Everything we know to be correct. So in fact, it basically says that with all the knowledge that you have, can you prove primes are infinite? So if I have to prove this statement using the contradiction, how will we go about it? So one way of going about it is, of course, recall that we have to prove that this whole thing is congruent to not B and A. This is false. Right? Or in other words, this statement says that if B is not, if the number of primes is not infinite, or in other words, if the number of primes are finite, then something that we know must be contradicted. So there is something, so A here, something that we know must have a contradiction. Right? And this is how we will go about proving our statement. Okay, so let's continue with the proof. So let's assume that there are finitely many primes. So that means there is the largest prime. Let's call that one PT. And in that case, we say that the set of primes are the P1 to PT. P1, P2 till PT. Now consider this number, the product of all these primes plus 1. Now what is this number? First of all, note that this number is strictly bigger than PT. Why? If you remember that we know that P1 is 2, we know P2 is 3 and so on. So this number P1 times P2 2 times dot 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 till PT is bigger than twice PT or 6 PT and so on. Right? So that number, this number, product of all the PT things plus 1, if this one turns out to be a prime, then what happens? Then it contradicts the fact, first of all, that PT is the largest prime. We have assumed PT is the largest prime, so it contradicts the fact that PT is the largest prime. Because this one is clearly greater than PT. Now can or is the product of P1 to PT plus 1 a prime? Now if the product plus 1 is not a prime, then by the definition of a prime, something must be dividing it. And when something divides it, we have looked at this proof earlier, that if some number integer divides another integer, then there must be a prime that divides the other integer. So in other words, sum 1 of P1 to PT must divide the sum, because P1 to PT are the only set of primes that we have. But all the primes P1 to PT divides, of course, the product of them. So when we divide the product plus 1, this number, by any number, say, does P1 divide this number? When you divide this number by P1, what remains? The remainder is 1. Similarly, when I divide it by P2, the remainder is 1. Similarly, when I divide it by the prime PT, the remainder is 1. Or in other words, none of these primes P1 to PT divides this new number. So this number is not divisible by any of the old primes P1 to PT. What does it mean? It means that there is only one, that this number has to be a prime. There is no number, no prime can divide this number, hence this one is a prime. And this is a contradiction, as we have discussed earlier, because now we have a number that is a prime that is bigger than the largest prime, which cannot be. So this proves that our initial assumption of PT being the largest prime is false. In other words, there cannot be a largest prime. Or in other words, PT cannot be, or number of primes cannot be finite. So basically, we prove that if P1 to PT are the set of primes, finite set of primes. Then I created a new number which was larger than the largest prime, and we proved that it has to be a prime, which is a contradiction. Right. So this is a typical proof by contradiction, where we start from assuming that the statement that we have to prove is not true, and we work our way through, and at the end prove that it contradicts something. Either it contradicts what we are assuming, or it contradicts something that we know, and so on and so forth. There are many related problems to this particular problem, and I leave it to you as an exercise. For example, prove that there are infinitely many primes of the form 1 mod 4. So namely, what are the primes 1 mod 4? Say 5, 13, 17, 29, and so on. Prove that there are infinitely many primes of the form 1 mod 4. Similarly, prove that there are infinitely many primes of the form 3 mod 4. Again, similarly, prove that there are infinitely many primes of the form 1 mod 6, and there are infinitely many primes of the form 5 mod 6. So we will be doing some more problems using contradiction in the next video. So in the next video, we will be proving some statement like that square root 2 is not a rational number. Now, what is a rational number? A real number is rational if it can be written as ratio of two integers. So if a number can be written as p by q, where p and q are integers, then we say it's a rational number. Namely 1, 2, 3, so all of them can be written as 1 by 1, 2 by 1, 3 by 1, 2 by 3, 49 by 99, and so on. We claim that square root 2 is not a rational number. In the next video, we will be proving this particular problem using the same contradiction technique. I encourage you guys to go and try to solve this problem by yourself before you see the next video. Thank you.